Hi everybody, I'm James Weinert. I go by Jim. I'm currently a software developer at Carvana where I write Scala for their chat and SMS backends. Carvana uses the Zio effect framework for all of our new services, but a lot of our old services are still running on actors. Sometimes you don't need to use the latest and greatest. There are a lot of really good companies that have been built on actors. I've been using Scala and Go for almost a decade, and I love them both. I learned both Scala and Go at the same company, so I don't have a preference of one over the other. But today, I'm going to highlight one use case where Scala has an edge, its implementation of the actor model. So I wanted to show off why Carvana chose the actor model for its chat backend. Chat is incredibly simple to implement using an actor, like almost too simple to show off all the great things that actors can do. All it's doing for our chat backend is passing strings back and forth. And so I needed something a little bit more complicated with some more edge cases that are annoying to implement without using actors. My first thought was for a game, but it would need to be a multiplayer game, but without a lot of complicated logic. So if you already saw the talk title, spoilers, I wanted Quiplash. If you've never played Quiplash, it's a party game where players answer prompts and vote on who has the funniest answer. The best part of Quiplash is that everyone plays the game using their phone's web browser. Like, this is a perfect analog for Carvana's chat system. Carvana's chat backend needs to route messages from customers to our chatbot or customer support agents, and then route responses back to the customers while maintaining a little bit of state to provide context to the chatbot about where the customer is in the purchasing process. And today, we're going to make a Quiplash clone called JustClout. JustClout will be handling input from our players, updating the players when the game state changes, and maintain the current state to enforce game logic. The logic for JustClout can be defined as a state machine with these distinct states. First, you need to create the game. That's going to be a simple HTTP request to create our run loop and generate a unique token or game code that allows other players to join. If you've never played Quiplash before, you start a game on a computer or video game console that acts as the display. Then all of the players visit jackbox.tv and use their unique game code to join the game using their phones as their input devices. It's so much better than everyone needing their own controller. You can have so many more players than you would for a normal video game console. I think all party games should copy it. My only qualm is that having the computer as a display is very difficult to share over Zoom or Google Hangouts. If we were designing it from scratch today, I would have all of the game state displayed on everybody's browser. In the waiting for players state, the players can only do one thing. They're going to post to our backend with their unique game code and create their player specifying their name. If we wanted to add authentication, and I didn't in our example to save time, this is where you would set a session cookie or a JSON web token with that player's ID. In JustClout, a game typically consists of multiple rounds, with each round giving users 2 prompts to answer. Each prompt will have players going head-to-head to see who has the best answer. And other players will be voting on their favorites. Once you have implemented one round, it's really easy to add a second or a third. In the answering prompts state, each user will get 2 random prompts. We'll know to advance to the next state when all users have answered their prompts. After every request from a player, we can check if everyone has answered their prompts and advance to the next state. But we also want a timeout so that our players don't have to bug their slow friends. Up until now, we could have kept the entire state of the game in a database instead of using an actor. To advance the state without user input, we need a run loop of some kind. The run loop can start the timeout and trigger advancing to the next state. This is why an actor is a good fit for this. In the voting on answer state, The game will iterate through all the prompts, anonymously displaying players' answers for each prompt. Voting should have a timeout as well, but it'll be much shorter than when the players are actually answering the prompts. At the end of each vote, reveal who voted for who and score. And then we could tally scores as we go, but it's much cooler to cinematically tally the score at the end of each round. Let's have a state that returns everyone's old score and new scores after the round, and the UI can make it interesting. After scoring, we can loop through another round with all new prompts, or end the game. Once all the rounds are complete, display the final score, and give the users an option to play again with the same players. After starting the game's run loop, every state has a timeout that advances it to the next state except for the waiting for player state and the end game state. A game could get stuck in those two states waiting for player input. It's not important for our example, but if we shipped this, we'd want to garbage collect games that were idle for too long without any player input. If you are watching at home, now would be a good time to pause the video and try and implement this yourself in your language of choice. And if everyone has their version running, let's look at how I would implement this in Go and Scala. So first, let's talk about concurrency. What does concurrency look like in Go? Go has an implementation of microthreads called Go routines. Go routines are lighter weight than threads. They're faster to create, and you can have way more Go routines than threads. You're only limited by system resources, so you can have hundreds of thousands of Go routines running simultaneously on a single system. Go routines are created by invoking a function using the Go keyword. In this example, we are executing the function doWork, which will run parallel with other Go routines on the system. Running in parallel does not mean that your code is running concurrently. On a single CPU, only one Go routine will be running at any time. Here's another example of an anonymous function, here's an example of an anonymous function to execute code on a Go routine. Adding the parentheses at the end of the function definition causes it to immediately invoke. If you use modern JavaScript, you're familiar with this. You know all about IFEs, immediately invoked function expressions. One other thing to remember when using Go routines is that the variables in your scope might change by the time your Go routine executes. If you want to use a variable inside an anonymous function, pass it as a parameter. The example on the left is likely to print 5 times, because by the time the scheduler switches to execute the Go routines, the for loop has already iterated through the entire slice and n is equal to 5. Go routines aren't free. Creating them still has a cost, and the best way to optimize your Go code is to reduce the number of allocations, including Go routines. If you want to execute a bunch of Go routines in parallel, your program will be more performant if you create a pool of Go routines and send work to them. For JustClout, we could create a Go routine for each game's run loop, and then every request from a user will use a channel to send the payload to the Go routine. Channels are a thread-safe way to pass variables between Go routines. Here, we're using a channel called in that passes ints, and using it to send values to the Go routine doWork. Channels will block when pushing or reading a variable until the other side of the channel reads or pushes the variable. Here, doWork is looping over any values that are passed to the in channel. It'll block until a variable is pushed. If we were to move the doWork Go routine invocation to the end of the main method, the program would block and never execute. As soon as we try to push the first one to the in channel, without any active readers, that would block forever. If you don't want blocking channels, Go also supports buffering channels. By adding a length when we allocate our channel using make, we've created a queue that can hold up to 10 ints. If a buffer is full, we go back to the previous behavior. The Go routine pushing the value will block until an int is read off of it. Because Go routines are so performant and each JustClout game has a tiny number of users, we won't need to worry about buffering any of our channels. If you ever need to read from multiple channels, use a select statement. Whichever channel unblocks first will resolve the select statement. The for loop in this example ensures that doWork is always reading off of the in channels, since the select will resolve and then exit. Channels are built into the language, and Go handles all of the locking for you. Because it's built into the language, Go can make some crazy optimizations. like having one Go routine write into the memory of another Go routine's memory because it has guarantees in the language that the other Go routine is blocked. What we do need to worry about, though, is returning a response to the players. One problem with channels is that they pass the variable and then resolve. There's no way to send a variable to a channel and then wait for a response. We could accomplish this behavior with channels, but we would need to include a response channel in the payload that we send to the Go routine. It makes the code just complicated enough that someone reading it for the first time might not understand it. If JustClout was a more complicated game, this would be fine. But JustClout doesn't have any computer players. The only input we have is from players and timeouts. Let's use mutexes. They're faster than channels. They're straightforward, and they're not as terrible as mutexes are in other languages because Go has the defer keyword. The defer keyword is going to execute whatever function is passed to it at the end of the current function returning. So here, by calling lock and unlock right next to each other, we're less likely to forget an unlock call and run into a deadlock. Because the entire function is covered by a single mutex, we're less likely to have a deadlock from nesting mutexes that could block each other. We'll add a mutex in our JustClout to any struct whose methods need to be called by different Go routines. So let's talk about Scala concurrency. Supporting concurrency in your application is difficult because of shared mutable state. You need to worry about other threads or microthreads making a change to a shared variable, which can cause either race conditions or corrupt data. Scala's solution to this is to make variables immutable by default. If you don't have a mutable variable, you can't have shared mutable state. All of the data structures are designed for it and are very performant. But let's talk about what other options are in Scala, even though we probably won't use them. So Scala has mutexes. The synchronized keyword is built into the language. It lets you turn any variable into a mutex. We are not going to use it. Up until Java 21, Java didn't have microthreads built into the language. Java 21 added Loom. Frameworks are still kind of adopting it. The go-to web server Netty has a version that uses Loom, but it still needs further optimization to beat the old versions in all benchmarks. I'm looking forward to mainstream Loom. I want to use it, but we're not going to use it in our example. And then futures. Futures are Scala's versions of callbacks. You can combine, map, and filter futures just like Scala collections. To resolve a future, use the onComplete handler and then add your logic to the callback. I like to think about functional programming as like a Rube Goldberg machine. You write the individual components, and because your components are pure functions, the same inputs generate the same outputs without because your functions are pure functions where the same inputs generate the same outputs without any effects, any component can be easily swapped out for another. And so you hook them all up in your main method, and then you press the button that kicks off this cascade of resolving logic. But futures break this. Scala's futures require the execution context to be declared at compile time instead of runtime. So you'll see us passing around the execution context using implicit variables. If you're unfamiliar with implicit variables, it's a way of declaring a function parameter. Because the value of an implicit is the only one of that type defined in the scope, the function will use it without having to explicitly pass it to a function. So next, we have actors. The simplistic way to think about an actor is a thread-safe object. Instead of calling functions on it, you send it messages. The messages are put into a message queue, and the actor avoids concurrency bugs by executing only a single message at a time. There's no shared mutable state. The actor system maps the actors to threads, just like microthreads do, allowing us to run hundreds of thousands of actors at a time, just like the Go routines. Also like the Go routines, the only limit to the number of actors you can run in your system is the amount of system resources. There are multiple libraries that implement actors. We're going to be using Apache Peko for JustClout because it's new and shiny. So let's look at the implementation of a really simple actor. Here are the imports that we'll need for our example. so that you can have all of the code. A quick overview of types, if you're not familiar with Scala. Objects, like the object counter defined here, are never initialized. All of their methods are static. You usually put the helper methods for your case class into an object with the same name. These are called companion objects. Here, the apply method is acting like our constructor. If we call counter with parentheses, the apply method will be invoked, creating a new behavior of type command. Case classes are like regular classes, but immutable by default. They're compared by value instead of reference. This makes it really easy for Scala to compare case classes and to use them in pattern matching. Here we are pattern matching in the behaviors.receive message. Each of the case statements is like a case statement in a normal switch, but Scala's pattern matching is capable of decomposing the parts of the case class into variables that you can use in that case statement. And then a case object is a case class that has no values. So this is a simple actor that can accept 3 types of messages: one to get the current value, one to increment it, and then one to increment it by a specific amount. All of our messages are inherited from the trait command. A trait is like an interface in Go or other languages, but in Scala, traits can have values and methods associated with it. So making the trait command as sealed means that nothing outside of this scope can extend it. This lets the compiler guarantee that match statements can cover all of the possible case classes when pattern matching. If our pattern matching does not handle a possible message and the actor receives that message, it will throw an exception. PECO actors work great as state machines. We're storing our state in the current behavior. Sending the message current value doesn't make any changes to the behavior. So in the case statement, it is returning behaviors.same. I guess I should say that behaviors.receive message takes in a message and then returns behaviors of type command. Increment and increment.By alter the state of the actor. So we call the same method that we use to define the behavior, but with the updated state. In the current value case match, we include a variable reply to. It's a reference to the actor that sent the message. And then here it's an actor expecting a return of type int. And then when we send the reply to exclamation mark, the exclamation mark is sending the sum in response to the actor that sent this message. To send messages to this actor, we need to create an actor system and initialize a root actor. In our case, we're calling the variable counter. There are 2 ways to send messages to an actor. The exclamation mark operator sends a message to an actor asynchronously. It's called fire and forget. It doesn't wait for response, and the code continues to execute. The question mark operator, which is also an alias for the ask method, will block until the actor responds. Because ask is blocking, PECO requires that we provide variables for the timeout in the scheduler to the ask call. We're defining them as implicits, so we only need to declare them once. We could make them regular variables and pass them in to the ask method. Notice that we don't set the reply to variable in current value. In the current value case class, when we call counter.ask, the ask method will automatically add the actor ref to the end of our parameters if that message can accept it. The ask method returns a future. In here, this would be a future of an int, and we need to handle the success and failure cases to use the response from the actor. Now that we have like a thread-safe state machine, we can use that to implement our just clout. You don't have to create an actor from scratch. PECO provides templates for you. If you have the Scala build tool, SBT, installed, you can run the following commands. Just clout will be using the PECO HTTP quick start template. Both of our services are going to have the same structure. Both of them are going to have an HTTP handler. In Go, these are called, or they're going to have the same HTTP server. In Go, this is called a handler, And in Scala, we're going to call it a routes. To handle requests from a player, if we wanted to add authentication or create a session cookie or a JSON Web Token, we'd be adding it into this part of the code. All routes should return the public game state to the user. This is going to be different from the actual state of the game because players will only see a subset of the current state. Players answering prompts will only see their current prompt, and then players voting on answers should not be able to look at the network requests and see whose answer they're voting on. We're going to have a manager, which is responsible for creating new games or routing player requests to each game. There'll be multiple games running at a time, so this part needs to be thread safe. The run loop is going to take a player's request and execute the correlated method in the game instance. It's also going to track any state change caused by a timeout. There will be multiple players executing commands in a single game, so this part also needs to be thread safe. The instance is the logic of the game and also the current state of the game. Just clout games are really short. We don't need to persist any data to a database, but a more complex game might need to. The instance is where you would put that code. If the run loop ensures that only one user is updating the instance at a time, then we don't need to worry about the instance being thread safe. So let's look at some code. First off is going to be the HTTP server. We're going to need 3 routes to create the game, get the game's current state, and to execute a command from the player. Go has an amazing standard library. Its HTTP package is going to be faster than any third-party HTTP package you could use. We are going to be using the Gorilla Mux library, which makes it really easy to pull variables out of the URL path. Here is how we create a handler for each method, for each path. /game is going to invoke the create game function when the method is posted to. /game code is going to do the same thing for the get, state, and exec command functions depending on the HTTP method. All of the Go handler functions are going to have the same parameters. A response writer for writing bytes back to the client and a request struct to read bytes from the client. Go really is just passing bytes back and forth. Once you start writing bytes to the response writer, Go will stream those bytes to the client. At that point, you can't change the status header because it's the very first thing that you send on an HTTP response, and Go has already sent it. If you didn't set it using write header before then, it's going to default to a 200. Create game is our simplest function, but we still need to manually check all the errors and set the response content type. And we're going to have to marshal our response into JSON. When we get the current state of the game, when we're calling get public state 0, we're passing 0 in as a parameter. Go doesn't let you overload methods, and I wanted to avoid using an int pointer. Go does set default values for all variable types, 0 being the default for an int. And so for get public state, we are passing an int for the player ID. In get game state and exec command, we're going to get the player ID out of the request. Pecco has an HTTP library built on top of actors, perfect for our use case, called Pecco HTTP. It's got its own unique DSL, or domain-specific language. I'm not going to get into the details of that, but there's a link to the documentation showing you what it's capable of. Here's what the route's going to look like. Create game is using ask to message the actor for the manager. The route has an onSuccess handler for it, and then onFailure is automatically going to return a 500 status for us. To handle errors, we're going to wrap the response from the actor in a status reply. Usually I would throw an exception and then wrap it in a try, but actors are meant to crash on failure. But when the actor does crash, it loses its current state when it restarts. So we need to make sure that we catch all possible exceptions inside our actor so that we don't lose the current game's state. I really need a better place for this guy. So this does everything that we need. Complete will automatically marshal our response into JSON as long as we define implicit JSON encoder and decoders. We do that in a different file for the public game state. Here's the entirety of the handler method for Go and the routes.scala. So let's compare how many lines of code the definitions are for each. Like, they might look comparable, but the Go version is a lot longer than the Scala version. Pecco HTTP routes are more complex, but once you learn the DSL, it's a lot faster to add new routes. Following the user's request, next up is going to be the manager. The Go manager has 3 public functions, one for each corresponding route. In Go, if a function or variable starts with a lowercase letter, it's private. When it's capitalized, it's public. These are the only public methods for a manager. We need to use mutexes when we retrieve the game from the map of run loop instances. I prefer to use defer statements when creating a mutex. Put the unlock call in a defer, and you'll always know just by looking at your lock call if you did or did not unlock that mutex. Concurrency bugs are really difficult to track down, and we need to make it easy for ourselves. We could wrap the entirety of the get public game state and exec commands in a mutex, but then we'd be blocking other players in different games when they are trying to access their run loops. Since run loops have their own mutex, we can move the map access to its own helper method, getGame, and we'll make it private. In the exec command, the manager is sending the commands directly to the run loop to keep as much logic as possible out of the handler, which should only be handling the requests, and out of the manager, which should only be creating games and routing commands to your run loop. The Scala manager has the same actions, but instead of functions, they're going to be messages that we can send to the actor. Each command has an extra parameter, the actor reference to the route that's sending the message. If you use .ask, it will automatically add the actor's reference as the last parameter of the message. We're going to create an actor that stores the games as a map with the game code as the key and an actor ref as the value, the actor ref of the run loop. If we were using a Pecco cluster, there's a way that we can create child actors and then find them using an entity ID, which is just a string key that could be our game code. But setting up clustering is way more difficult and out of scope for this example. Maybe version 2 of this talk will clean that up. Here, when we're defining our actor's behavior, we're calling behavior.setup because that passes the context. We're going to need the context for the manager so that we can create new child actors or get the current execution context for any futures that we're going to run into. And then we handle the create game message. When we handle the create game message, we're using our actor's context to create that new child actor using .spawn. We want to return the public game state to the player. So a get state message is sent to our newly created actor. We're passing none for the player ID and the reply to variable, which is the actor ref to the route making this request, which is waiting for a response. Here, the message is going to be fire and forget. The manager is only processing one message at a time and can get to the next message that much faster. It doesn't care what happens as long as the run loop is responsible for responding to the route. And then finally, we update the current map of games by creating a new map that includes the new child actor's key value pair. We update the behavior with the new map. Next, we have the run loop. Here are some of the commands that we can send from the front end. I wanted Go and Scala to have the same JSON payload, so I only have to write one front end, and then that way you can more directly compare the two. Go handles missing values from the request struct by having defaults for every type. The uint64s will be 0, the pointers will be nil. Scala handles missing values by, we're going to make every field an option and then default it to none, a missing value. Error handling is slightly different between the two implementations. In Go, the command is passed directly to the run loop. Here, we're validating the parameters and returning an error if the player struct is missing from the request. If add player fails, the error is returned to the manager, which returns the error to the handler, which should return a 400 to the user. Every command should return the current state, and so at the end of this code, we make that call after we've updated the state of the instance. Since getState can't return an error, we return its results directly without checking for any errors. In Scala, we need to convert the request payload, the manager command case class, into a run loop command message that we can send to the run loop. If the request is invalid, we're going to throw an exception, but we absolutely don't want to throw an exception in an actor. The actor will restart, it'll lose its current state. And when I was testing this, I suspect it gets a new actor reference because the way I map a game to code to the actor ref stops working once an exception is thrown. So what we need to do is wrap our code in try. Here we pull the game out of the game map using the unique game code that we sent in the message. And then we send the message to the run loop actor, which will respond directly to the routes. Any errors we encounter, we wrap in a status reply, and then we send it back to the route. This works. The route knows to return a 400 for any of these errors. And here is the behavior for the run loop actor. Because adding a player can fail, we want to wrap calling add player in another try. If adding a player succeeds, we update the behavior with the new state of the game instance that's returned by add player. Otherwise, we return an error and keep the same behavior. So let's talk about that new instance. We don't need to go into detail on the logic in the instances, but there's some important differences between the Go version and the Scala version. In Go, we create a game instance and make changes directly to that struct. Here's how we would add a new player to the slice of players and increment the next player ID, the counter that we're using to track which ID we should use next. We're making changes directly to the instance variable, to the variables in the instance struct, because everywhere is using instance as a pointer. Anything with a reference to that instance is going to see these updates. For our Scala instances, we're using case classes which are immutable. Instead of mutating our instance, like any methods that update the state are going to return a copy of the current case class with the updated values. Here, we're doing the same thing as the Go version, adding a new player to the player list and incrementing the counter that we use to keep track of the player ID. We'll return a copy with all of the other fields. And then our run loop uses the new instance returned by add player to update its behavior. The final difference that we need to cover between the two versions is how they handle timeouts in the run loop. So once a game is started and we've finally progressed to the answering prompts state, players will have 2 minutes to answer prompts before the game moves on to the next state. When the state starts, we're going to need to trigger a timeout. We can do this with a Go routine and calling Go's sleep function. This function will block until time.sleep completes, but because it's running on a Go routine, we don't have to worry about it blocking. If you notice, we are passing some parameters to the advance state function to handle some edge cases. Whenever we perform work asynchronously, we need to worry about what happens when that asynchronous work completes before, during, or after other work. If the timeout fires before the users finish answering their prompts, that's expected behavior. We want the game to advance if players are slow. So the game advances, the players face some consequences. In Quiplash, they end up getting a random computer answer, but we could do whatever we want. Because we're using mutexes, the second case, the advanced state will never execute in the middle of the run loop functions. So we don't need to worry about that. What we do need to worry about is what happens if advanced state is called after the game has already progressed. When all of the users answer their prompts, we want to immediately transition to the next state. We don't want players waiting needlessly for the timeout to fire. So we include the current state, answering prompts in this case, as a parameter, and then in our advanced state method, we're going to have to check to make sure that the current state of the instance matches the current state for when the timer was created. If the current state and the state the timeout is expecting differ, nothing happens. The current voting prompt parameter is for timing out when players are voting on answers. In the voting on prompt state, calling advanced state should move it to the next prompt, not end the state. And so we're keeping track of the ID of the current prompt being voted on. The scoring round is also going to have a timeout, but players can't execute commands during the scoring round. It only needs to run long enough for the front end to poll and animate something fancy. For the Scala timeouts, we're going to need to create new messages for our run loop actor that can fire when the timeout completes. Since the messages don't have any values, they can be case objects. Actors have a pipe to self method that we can use to send messages when a future completes. The first parameter of pipe to self is a future, and the second parameter is a function that maps the results of that future to a message. This is great for network requests, but can also work great for our timeouts. We can create a future that does nothing except sleep for the duration of our timeout. And then because we're using a future, we need to have an execution context in our scope. Here, we're using the execution context of the current actor, and we're defining it as an implicit variable so we don't have to pass it. Notice that the final pattern match is a case underscore. The underscore will match against any messages that are not matched by the previous cases. Thus, any messages that we can't handle, we just drop. The behavior of the actor stays exactly the same in those cases. Also notice that when we change the behavior of the actor to advance the state, we're calling a different function to define our behaviors. Instead of calling players run loop, we're calling answering run loop. Well, we can have different functions defining the behaviors for each state of our game. The player's run loop will only ever respond to messages related to adding players. The same for the other states. Thus, like the answering run loop is going to be the only set of behaviors that will respond to the answering prompt's timeout message. If the timeout message happens after we've already transitioned to a different state and a different set of behaviors, that message will get dropped. We don't have to pass any state to our timeout or perform any checks when the timeout fires. We either process the message or we drop it, and I think that's beautiful. So that was the last feature of actors that we needed to cover to successfully implement JustClout. The rest of the implementation is just repeating everything else that we've already discussed. So now we have two implementations of JustClout, each with their own trade-offs. For JustClout, I'd pick Scala, but like a developer could be happy with either of the implementations. Some of the other trade-offs that we didn't go over. Go is really straightforward. Like it's basically a better C. It's imperative. Once you learn the basics, you can be productive in a couple of weeks. And I do want everyone to be aware of complexity. Like by adding Pecco actors, you're adding a system to your application. When it works, it's great. But when you have to debug it, you're going to be reading a lot of docs about config settings that you really shouldn't care about. And worst case, you might be reading source code to try and figure out how the actor is actually behaving. Scala has a huge learning curve. I think it took me a year before it finally clicked for me. But once you're up to speed, you can write so much more with so much less code, sometimes. Scala is really good at transforming data. I can write an anagram solver in 10 lines, but I still haven't found a database ORM that I like. We use Quill at my current job. It's better than the others. but I'd rather still just write SQL. Go makes it easy to optimize. It also makes it like really easy to tinker with performance in ways that don't matter. In JustClout, we could reduce the allocations in our handlers by using a sync.pool to store a buffer of bytes buffers. Instead of allocating a new bytes buffer anytime we're marshalling JSON, we could pull a buffer off of the pool, and then we wouldn't have to perform an allocation on it. Like, it's fun to improve benchmarks, but like Go is already so fast that it doesn't matter for the JustClout users. Like Go services use an incredibly small amount of memory, only like hundreds of megabytes. If your VM has 2 CPUs, you can get the number of GC pauses down to 0 by reducing the number of allocations. Like, tinkering's fun. You got a lot of options there. The best and worst parts of Scala are that it's a JVM language. On the plus side, you have access to every Java library, and there is a Java library for everything. On the other hand, now you have to worry about null variables and throwing exceptions, and it's undoing all of Scala's type safety promises. And because a Java library exists, no one's going to make a Scala library for you. Like, mixed bag there. Go also has really great tooling. I'm pretty sure our implementation of JustClout doesn't have any race conditions. And like, I can be that confident because Go has a -race flag that you can add to your build command or when you're running your tests. And it'll detect race conditions for you and let you know if one exists. And then Scala makes you feel smart sometimes. Like, I still have to look up what the different types of variants are, but like, sometimes you solve a problem with a solution that just like makes you feel good and you get a gold star. Go and Scala both have garbage collectors. Like, JustClout isn't resource intensive at all. It's entirely turn-based. GC pauses aren't going to drastically affect the gameplay. But like, if the game was real time, your players would rage quit the first time they hit a GC pause. So like, why didn't we include Rust in our comparisons? Like, Rust is also a very exciting language. Like, it doesn't have a garbage collector. It has multiple actor implementations. And I'd love to compare. I would love to compare a Rust version of JustClout to the Go and Scala versions, but I don't have the experience with Rust to do it justice. Maybe one day. Thank you. That's the end of my talk. Thank you for coming. The source code will be uploaded to the JustClout GitHub page as soon as I have a secure internet connection. It's not a complete implementation of JustClout, but just the things that we covered. I'm counting to 10 on almost all social media platforms. I use Mastodon the most. If you enjoyed my talk or you think I should have implemented something differently, I would love to hear from you. And I hope you have a great LambdaConf. We have 7 minutes. We can either do questions if there are any, or we can go to lunch. Yes?
Did you consider doing a Zio version or some other effect version of this?
I did. So the question was, did you consider doing a Zio version of this? And I did not, because I wanted to show off actors, and the Zio actor, I don't think it's been updated in over 2 years. But you could probably have the exact same implementation if you were using Zio's ref to control your state for you.
Yeah, maybe Zio stream somewhere there.
Yeah. Any? Yes.
So I haven't used actors before, or specifically the Peko actors. When you're blocking on that request, what is that blocking? It didn't look like a flat map. Are you actually like blocking a thread when you're saying like, hey, wait for response?
Cool. So the question was, when you are blocking in an actor request, what are you blocking? Inside, that's a good question. It is blocking the thread, but inside the actors, you're using the internal microthreads that the actor is doing. And so if you're doing that in your main method, it's probably going to block your primary thread, but if you do it inside an actor, it's not going to block any other execution.
Okay.
It's just blocking that one microthread that the actor is using. Cool. Thank you all for coming to my talk.